All right, welcome to the lecture over 3.4, Composition of Functions. This is a 7 a.m. lecture, and I'm the only one in the room this morning. Go figure. Anyway, since I'm the only one in the room here this morning, I'm going to try my best not to go too quickly and try to think of questions that students normally have over this material. So hopefully I'll live up to that expectation. Okay, so the first thing that we encounter in this section is just what is the whole idea of composing functions. Okay, so let me get my pen going here. Okay. Function composition is only one way to combine existing functions. We can actually carry out other algebraic operations such as adding functions together, subtracting, multiplying, and dividing. And this is done by just performing those operations with the function outputs. And we define that result as the output of our new function. Okay, so let's get back to, composition of functions. What is this thing that we can do called composing functions? So if you look to the left of the screen here in the gray box, a general note about composing functions. When the output of one function is used as the input of another, we call the entire operation a composition of functions. One way of saying this is you are plugging in or substituting one function into another for the variable. And when I teach composite functions, I like to talk about the idea of a shell function and a plug-in function, because you're going to have one that plugs into the other function, and then you're going to have one that acts like a shell. It houses the other function within it. So, pardon me. This F with a little, looks like a degree symbol between, and G, this is just saying compose function F with function G. So this says compose function F with function G. Whatever is listed first, so in this case is function F, and let me color code this. Function F is listed first. Function F, since it's listed first, is considered your shell function that you're going to plug the other function into wherever you see the variable. So my shell function is always listed first. Okay, and then I have my plug-in function. And by the way, these words I'm using, I made these up. So don't go asking a tutor, what's a shell function? What's a plug-in function? This is a Libby-Gore-ism right here. So whatever function is listed second, that's your plug-in function. And this will make a lot more sense when you actually see this happen here on the next slide. So, your plug-in function is listed second. And so once again, all this means is in the F function, you're going to be given the actual function. Wherever you see X, you're not going to plug a value in necessarily. You're going to plug in another expression, another function into the shell function. And then an important word about domain and range with composite functions. The domain of the composite function f of g is all x such that, okay, this is important, x is in the domain of g, so it's able to be input into the g function, and whatever comes out of the g function, the output has to be in the domain of f because you're plugging that into f. So you're using the output of g as the domain for f. So you've got to check all this before you can talk about what is the domain of the composed function. It's important to realize that the product of function, okay, this is just, this down here, this is talking about something that's not even addressed in this section. This is talking about these other operations that can be done, and I guess the textbook authors just thought it was important to point out, because when you multiply functions, you literally multiply f of x times g of x. This is not the same thing as writing it this way. That second thing written here, that's composition of functions. So two different things going on here. And then this little image off to the right here just shows you again that when you're composing functions, you're plugging one function into another function. So let's see how this actually works. And I'm going to keep all this color-coded. It takes a little bit more time to write it out, but it really helps you see what's going where and what's happening with it. So I encourage you on your own to maybe grab some colored pencils or pens and see if that helps you out as well with composing functions when you're working through your homework. Okay, so we start off by being given two functions, and we're asked to determine, is the composition of these functions commutative? In other words, can I plug g of x into f of x, and can I plug f of x into g of x and end up with the same thing? So I will use this magenta color for f of x, and I'll use my blue for g of x. So the first thing that we are asked to give a try is f composed with g. That's fog. And it's not really an O, it's more like a degree symbol, like 62 degrees Fahrenheit, that type of degree symbol between them. But it means compose F with G. In other words, remember, whatever's listed second is your shell. So this is what this actually looks like. It says, I'm sorry, whatever's listed second is your plug-in. So what this says is take the f function and plug the g function into it wherever you see the variable, and then see what you get for the expression. So that's what I'm going to do now. Okay, so my f function is 2x plus 1. So I want to write it shell, since it's the shell function. It's the one you're going to be plugging into. I don't write x, though. I leave room to plug the other function in for x. So 2 times something plus 1. And that something is the other function, 3 minus x. So can you see how color coding helps you see what's going on with this? Okay, now I've got, to simplify this expression, I've got some distribution to do here. And that leaves me with 2 times 3 is 6, 2 times negative x is negative 2x, and then I have a plus 1. So f composed with g is, we'll write it in slope-intercept form because that usually makes people feel good. We can also call this standard form in this case, negative 2x plus 7. Okay, so that is F composed with G. Let me note that we're done with this one. Okay, so let's see how G composed with F differs from that. G composed with F. Okay, this time, since the G function's listed first, this says G is now my shell function, and I'm going to plug my F function in wherever I see X in the G function. So this is what this looks like. G is now my shell. So 3 minus something. And the something that I plug in is 2x plus 1. Okay, so I'll just point out that there is an understood negative 1 that's going to get distributed to those two terms. And when I do so, I have 3 minus 2x minus 1, and that leaves me with negative 2x plus 2. Okay, so let me label this. This is G composed with F. All right, so the question is this operation of composition commutative? In other words, did you end up with the same thing when you composed F with G as when you composed G with F? I'll just remind you of the commutative property. Multiplication, for example, is commutative. 2 times 3 is the same thing as 3 times 2. They're both 6. They're considered commutative. You can commute the factors and end up with the same thing, end up with the same product. Composition is obviously not commutative because we've ended up with 2 different expressions here. So not commutative. All right, so in answering that question, you were able to practice here composing functions both ways, F with G and G with F. All right, let's look at this next example here. The function C of S gives the number of calories burned. Okay, so C of S, the function output, gives the number of calories burned completing S. Okay, so we've got our variable S defined here as sit-ups, how many sit-ups. And S of T, so here's another function, gives the number of sit-ups that a person can complete in T minutes. So we've got 2 functions happening here, and good thing because we are talking about composition of functions. So I'll write first, we have the function C of S, and this gives number of calories burned by S sit-ups. And then I have the function S of T, and this gives the number of sit-ups someone can complete in T minutes. And then we're asked to interpret, okay, well, if that's the case, what does it mean to write the composition C of S of 3? Okay, so inside the S of T function, the blue function, we know that T is standing for minutes. So with this function here, we're talking about 3 minutes. Okay, so what happens in 3 minutes? This entire function says since C of S, the purple function or the magenta function, is the number of calories burned, this composed function is the number of calories burned by the amount of sit-ups that can be done in 3 minutes. So you can see that it took the original two functions, the amount of calories that can be burned by a certain amount of sit-ups, and the number of sit-ups that someone can complete in T amount of minutes. And it crammed it together, it composed it, and then input a T value of 3 or a time of 3 minutes. So when you compose that function, it's got a new meaning. We don't have these two separate meanings happening apart from each other, but rather working together to create this new meaning of the number of calories that can be burned by the amount of sit-ups that can be done in 3 minutes. Let's look at this last one. Suppose f of x gives miles that can be driven in x hours. Let's go ahead and pull out this information. F of x is miles driven in x hours. And g of y gives the gallons of gas used in driving y miles. Okay, so it asks you which of these expressions is actually meaningful. So let's take them each separately. F of g of y this says this is an expression for the miles driven being determined by the miles you can drive or the amount of gallons of gas. Let's see, gives the gallons of gas used in driving a certain amount of miles. So it's determined by the amount of miles driven as a function of gallons of gas used. Miles driven by gallons of gas used. In other words, this particular function says, can you determine the amount of miles driven by knowing how many gallons of gas is used and how many miles you can drive on those gallons? And yes, that seems to be a meaningful expression. Now let's think about it the other way. G of f of x okay, so what this is saying, so the F is miles driven in X hours. So this is saying, can you determine Okay, so G of Y is the gallons of gas used in driving Y miles. Can you determine the gallons of gas used by knowing the miles driven over Y hours? And I would say that you actually cannot. The f of x function is miles driven in x hours. So I drive a Nissan Xterra, and I get 18 miles to the gallon, roughly, with my truck. So would you be able to know how much gas I used without knowing what I normally get miles per gallon wise? Would you be able to know how much gas I used if all I told you is I drove, let's see, 300 miles in 5 hours? Would you be able to tell how much gas I used? The answer is no. So this expression is not very meaningful for us. However, the first expression is. All right, hopefully that's clear to you. Okay, so I felt it important to include this Q&A from your book. Occasionally they will put these little help boxes for commonly asked questions by students or common misunderstandings. So the question is, are there any situations where f of g of y and g of f of x would both be meaningful or useful expressions? And the answer is yes. For many pure mathematical functions, both combinations make sense, even though they usually produce different new functions. In real-world problems, functions whose inputs and outputs have the same units may give compositions that are meaningful. Remember this in the last example we looked at, the input and output values didn't have the same meaning. So that's why when we flip-flopped them, you don't get meaningful compositions both ways. Okay, evaluating. Evaluate, don't forget, means to plug something in and simplify it out. We usually end up with just a number answer, but you can evaluate using an expression as well, and you may end up with variables in that expression. So once we compose a new function from two existing functions, we need to evaluate it for any input in its domain. Oops, I grabbed a white pen, and you cannot see a white pen. Domain. We will do this with specific numerical inputs for functions expressed as tables, graphs, and formulas, and with variables as inputs to functions expressed as formulas. In each case, we evaluate the blank function using the starting input and then use the inner function. Okay, we evaluate the inner function using the starting input and then use the inner function's output as the input for the outer function. And I know that's a mouthful, but it goes back to on our very first slide regarding this information, talking about domains, that to be, let me go back to this so it will help us understand. Okay, so this is what's being highlighted right now. To be in the domain of the shell outer function. So in this case, to be in the domain of f of x, because you're plugging in an entire other function, you have to be in the domain and the range, or the input and the output of the plug-in function. Because if you're not in the input of the plug-in function, you can't even be input into that g of x function. And then whatever you get out as the output g of x, that is what's actually plugged into the other function. So the output of the plug-in function has to be in the domain of the shell function. Sorry, I went one too far. Okay, so that's what that paragraph is talking about. Evaluating composite functions using tables. So we're going to look at evaluating a different way here. Let me get my black pen again because it will not be fun if I'm writing in neon green. All right, once we compose a new function from two existing functions, we need to be able to evaluate it for any input in its domain. We will do this with specific numerical inputs for functions expressed as tables, graphs, and formulas, and with variables as inputs to functions expressed as formulas. In each case, we evaluate the inner function starting with the domain and then use the inner functions. Let me change the words instead of domain and range. Let's use input and output just to be clear. Starting using the starting input or domain and then using the inner function's output as the input for the outer function. Okay, so here we go. Let's do this using a table. We are asked to evaluate first, and let me color code this again. We'll call f of x. We'll do that in magenta, and g of x will be done in blue. Okay, so what these double tables are saying to you is we're using the same input, x, into each of these different functions, and this is what you get out, the f of x column and the g of x column for that particular function when you plug in the same x. In other words, if I plug 1 into the f of x function, I get out 6. If I plug 1 into the g of x function, I get out 3. So it's using the same x values for two different functions. So the first thing we're asked to evaluate is f of g of an x value of 1. Okay? So what this looks like, we first need to evaluate g of 1. So I still have my outer shell function holding on. And g of 1, okay, so what this chart shows is when I plug 1 into the g function, I get out 3. So I can rewrite that g of 1 is 3, so I can replace it in my shell function. I can now say, well, that's 3. So what this second part to the composition is saying, okay, now what's f of 3? So f of 3 is 3. And that's the entire composed function, or evaluating the entire composed function. Okay, so let's take a look at the next one. G of f of 4. So now f is my plug-in, g is my shell. So I'm going to start with my plug-in. You work inside out here. So f of 4 is 1. So what that's going to leave me with is g of 1, because f of 4 is 1. And then when I plug 1 in to the g function, once again, same thing. I get out 3. And that's evaluating that particular function. And then I just needed to fill up the rest of the slides. So I found this image on Google Images of how a composition of functions works. So hopefully that's helpful for you to see. X goes into the plug-in function. The plug-in function goes into the F function because it was F composed with G. Remember, it would have been just the opposite if it had been G composed with F. Okay, evaluating composite functions using graphs. Well, as we've already learned this semester, a table is no different from a graph, is no different from an actual function written as an equation. So this should not be a stretch of the imagination for you. It's doing the same thing we just did with tables, except now instead of a table of values, you've got graphs. But they're all representations of points. One's just visual, and one's in a table as numbers. All right, so when we are given individual functions as graphs, the procedure for evaluating composite functions is similar to the process we use evaluating tables. We read the input and the output values, but this time from the X and Y axes of the graph. Okay, so how do we do this? Given a composite function, evaluate it using these steps here. First, you're going to locate the given input to the inner, and we'll rename this inner function the plug-in. That's what we've been calling it. The plug-in function on the x-axis of its graph. So that's the input of the plug-in. And then we're going to read off the output from that plug-in function from the y-axis. You're going to use that output as the input on the x-axis for the outer function or the shell function. And then you finally read the output from the outer function from the y-axis. Okay, that's a lot of words. It's really not that difficult. It sounds difficult, but it's really not. I'm going to color code us again. So I have G as my shell, and this is actually a picture of the G of X function. And then I have F as my plug-in, so I'm going to start there. This is F of X. And the value that I'm going to be starting with is 2. Okay, so what the steps tell us to do, you start on the inside and work your way out. The first thing I want to do is find F of 2. Actually, let me write this figure off to the side. So we have G of F of 2. So the first thing that I'm going to evaluate is F of 2, and that's what I'm going to use as my input into my G function. So watch this. When I plug 2 into the F function, I get out 5. So F of 2 is 5. I can replace F of 2 in my composed function with 5. Now, my task is to say, okay, well, if that's the case, what's G of 5 then? So I go to my G graph and say, okay, if I plug in 5, into the g function, I get out 3. So g of f of 2 is 3. Takes multiple steps to get there. Okay, evaluating compositions using formulas. So we've looked at it with tables, we've looked at it with graphs, and now we're actually looking at the equation version of the function. So you're gonna do the same thing. You're gonna start with your inner function and work your way out. Let me color code. So here we have f of t, and I'll do the t in black. So my f function is magenta, and my h function will be blue. Okay, so the first thing we're asked to do is let me color code, is h of f of 2. So h of f of 2. All right, so I write my h function first. That's my shell. I don't write the x. I leave room to plug in. And what am I plugging in? My f function. So that's something squared minus something. And what it tells me to plug in, it doesn't say plug in t. It says go ahead and plug in 2 for t in your f function. So this is the expression that I'm going to be simplifying. So I start with the inside of my parentheses and exponents. 2 squared is 4, and then I have minus 2 plus 2. That's 3 times 2 plus 2, which is 6 plus 2, which is 8. So h of f of 2 is 8. That's my evaluated composition of functions. And B says, we'll do that same thing, but see what happens when you plug in -2. So that's the only thing different, is we're changing our input. Now what I could have done, I could have actually just seen what the composition was using variables, and then once I got my composed function, then I could go back and plug in 2 and -2. That's a different way of doing the same thing. But this works fine as well. So we're still doing H composed with F, so it's still, I still have my same shell and my same plug-in functions. The only difference is this time I'm plugging in -2. So this is what that looks like. 3 times something plus 2, and the something is something squared minus something, and the final something is -2. -2. All right. Let's see what happens. Okay, so I have 3 times. Well, -2 squared is still 4, except now I have a minus -2, so that's plus 2, and then plus 2 on the outside. So this is 3 times 6 plus 2, which is 18 plus 2, or 20. So H of F of -2 is actually positive 20. And I can't go off this page without showing this. I wasn't going to show it, but I feel like I need to. let's just take the general variable form of this. Let me open a new page here. Let me actually make a picture of this and take it to our next page. Okay, so watch this. If I just use my variables, I have h of, let's say it's just f of t. Okay, so this says 3 times x plus 2, and I'm plugging in t squared minus t. Okay, so just simplifying this expression, 3t squared minus 3t plus 2. That is my composed function. Now watch this. Hopefully this turns a light on if you're still a little bit confused about what's actually happening here. So if I want to do h of f of 2, I already know what my composed function is. Something squared minus 3 times something plus 2. In this case, I'm being asked to plug 2 into the composed function. So this is 3 times 4 minus 6 plus 2, which is 12 minus 6 plus 2, which is 6 plus 2, which is 8. Now look, same thing you got here, 8. Let's do it for the other one. So h of f of negative 2, we should expect to get 20 using the composed function, 3 times something squared minus 3 times something plus 2. And the something this time is negative 2. So we have 3 times 4 plus 6 plus 2 is 12 plus 6 plus 2, which is 18 plus 2, which is 20. Same thing. I'll just show you. Same thing. So you can either plug in and compose that way, or evaluate that way, or you can figure out what your composed function is first, and then you can choose to plug any value into that composed function. You're going to get the same thing either way. Hopefully that was helpful. Okay, a general note about the domain of a composite function. This is where it gets a little tricky to think about with the inputs and the outputs and all that stuff. The domain of a composite function, f composed with g of x, is the set of those inputs x is the domain, in the domain of g, for which g of x, or the output of g, is in the domain of f. So let me just point out that this right here is talking about the output of the g function. And that has to be in the domain of f. So to decide on your x's, the x's first have to be in the domain of g. And then whatever you get out after you plug those x's in, that's your output. That's got to live in the domain of f because it's got to be plugged into the f function. Okay, so you're going to find the domain of g first. You'll find the domain of f, and then you'll find those inputs that meet all those requirements, and I'll show you how. Okay, so first thing we want to do is to find the domain of each. So we'll color code again. F of x will be our magenta, and g of x will be our blue. Okay, so the domains of each of these. Remember, We have to watch out for two things so far, and that is 0 showing up in the denominator and negatives under even roots. So for f of x, the thing that I have to watch out for is that denominator being 0. So I set up that situation. When will x minus 1 equal 0? That's going to happen when x is 1. And then for g of x, I also need to worry about 0 in the denominator. So when will 3x minus 2 equal 0? Well, if I add 2, 3x is 2, divide by 3, x is 2/3. So, right off the bat, since our g is our plug-in function, let me just rewrite this up here. F composed of g of x, this is f of g of x. Actually, let me make that x black here. Yeah. Okay, so far, the first thing we want to do is figure out what we can't plug in to the plug-in function. So x at this point cannot be 2/3. Okay. All right, so if x is 2/3, then the entire thing is undefined here. So we cannot have, we know our composed domain cannot have 2/3 in it. However, we also cannot have the output, let me get my colors here. We cannot have the output coming from the g function equaling to the restriction on the domain for the f function. So we also need to figure out when will 4 over 3x minus 2 be equal to our our domain restriction in the f function, because we've got to plug our outputs from our g function into our f function as the input. So we need to figure out when is this going to happen, because this is going to be another restriction that we can't have. Okay, so I'm just going to point out that this is really 1 over 1. And now, since I have a proportion or two rational expressions being set equal to each other, I can cross multiply. So 4 times 1 is 4, and then I have 1 times 3x minus 2. Well, that's just 3x minus 2. Add 2 to both sides. 6 is 3x. Divide by 3. X is 2. So this is going to happen when x is 2. When x is 2, let me show you what this says. If I put, with my fully composed function, if I plug into g a value of 2, what's going to happen is I'm going to get an output of 1. And that's not good because 1 can't be plugged into the shell function. So I also have the restriction of 2 in my x values. So let me just draw a number line real quick, because remember, when we state domain, we state what it can be, not what it cannot be. Here's 0. Let's see, 1, 2. There's negative 1, negative 2. So 2/3 lives about right here. There's 1. 2/3 lives about right here. So what we have just figured out is that you can plug anything your little heart desires in except for 2/3 and 2. So I've got open circles on them, and then everything else gets colored in. If you can draw a number line of your solutions, of your domain, then you can translate it to interval notation quite simply. So the domain of f composed with g is from negative infinity up to 2/3 non-inclusive, or I can be between 2/3 and 2, or I can go from 2 to positive infinity. There's your domain. Let me just box it. All right. Okay, same two things here, just with different situations. All right, so my F will once again be magenta, and my G will be blue. Notice we're dealing with square roots this time. So the first thing we want to do is determine the domain for each function separately. So for f of x, what we cannot have is x plus 2 being less than 0. So that occurs when x is less than negative 2. So we don't want that happening. And then with g of x, and this is our plug-in, we have 3 minus x. We don't want that being less than 0. Subtract 3 and you get negative x less than negative 3. Divide both sides by a negative. When you've got an inequality and you divide or you multiply through by a negative, you've got to flip the sign. So this is x greater than 3. So right now, I'm going to just draw a picture of what our restrictions are so far. So far. Let's see. We have 0, 1, 2, 3, negative 1, negative 2, negative 3. Okay. So restrictions say with my f function, I cannot have anything less than negative 2. So the only things that I am able to have are things that are exactly equal or greater than negative 2. So remember, I'm drawing the domain. This is my domain so far. Not my restrictions, but my domain. So I'm drawing what I can have based on what we just found. And with the g of x function, I can't have anything greater than 3. So I can be equal to 3 or I can be less than 3. All right. So what we have to do, since I cannot have anything less than 2, strictly less than negative 2 in my f function, I've got to figure out, okay, well, when is the square root of 3 minus x, so the output from the g function, when will that be strictly less than negative 2? So when will the output from my g function violate the domain for my f function? So this is what I have to figure out. And to undo a square root, we square, but we got to square both sides. And so this is 3 minus x less than 4. Subtract 3 from both sides, and negative x is less than 1. Divide both sides by negative 1, so I'm going to go ahead and flip the sign. And this is going to happen when x is greater than negative 1. Goodness. Okay, so my new restrictions are when x is greater than -1, it's going to violate my domain, because my output from my g function will no longer be in the domain of my x function. I'm sorry, of my f of x function. All right, so I need to be exactly equal to -1 or less than that, because anything strictly greater than -1 is going to violate. So I can be exactly equal. Let me get my orange here. I can be exactly equal, or I can be less than. All right. The only places where all three domains overlap are from -2 to -1 inclusive. That's the domain of your composed function. So the domain of f composed with g is from -2 to -1, and I've got brackets on the end of both of those because you can include -2 and you can include -1. Let's just do a test. Let's choose, we'll choose -2 and just make sure everything works out okay. So, and I'm not going to color code this just for the sake of time because I'm almost at an hour and I've still got a slide to go after this. So f composed with g, that is equal to my f of x is my shell, so something plus 2 squared. And the something is the square root of 3 minus, and I'm going to plug in -2 for x. So -2. Oh, and it's going to give me a nasty, nasty number. Let me do -1 because that won't be as bad of a number. I wasn't thinking when I chose to do -2, so I'll do -1. All right. So f composed with g of -1, so it's a -1 in there. All right, so this is equal to the square root of 4 plus 2. The square root of 4 is 2 plus 2, and that's the square root of 4, which is just 2. 2 is a real number, so I'm good to go. If I choose, let's say, well, we'll leave it at that. All right, same thing for this last one here on this page. So I'm just color coding. First thing we need to do is figure out restrictions with f of x. So you see we have a denominator, so we got to be careful about that denominator equaling 0, and that's going to happen when x is exactly 2. And then g of x, we have a square root, so we have to be careful of x plus 4 being less than 0, so it being negative, and that's going to happen when x is less than -4. And now we need to figure out, okay, well, when is this g of x going to be equal to the restriction on my f, which is 2. So once again, I square both sides to get rid of that square root. And that leaves me with x plus 4 equal to 4. Subtract 4 from both sides. So we cannot have 0 either. So I'm gonna draw the picture of this. Let's see, 0, -1, -2, -3, -4, and 1, 2, 3. All right, so we cannot have, for our g function, we can have anything except values that are strictly less than 4. Oh, wait, I'm drawing not drawing the domain, but rather drawing the restrictions. Since we can't have anything less than 4, what we can have is exactly -4 and anything greater than that. So there's the domain for our g function. However, because even though 0 lives in the domain of g, when we plug 0 into g, we get out 2, which is a restriction on our f. So at 0, that is an open circle. Our domain is from -4 inclusive up to but not including 0, and then from 0 through positive infinity. There we go. Last page. Decomposing a function. So this is doing exactly opposite of what we've been doing. We've been plugging one function into another to create a new function, a composed function. Decomposing starts with a function that has already been put together, and you break it up into its 2 separate functions that it came from composing. All right, so in some cases it is necessary to decompose a complicated function. In other words, we can write it as a composition of 2 simpler functions. They may be blank than blank. There may be more than one way to do this. So just choose whichever one you see first. All right. So if I am being told that this f of x needs to be decomposed here with a, what I'm seeing here is that I have taken the square root of some other function. That's just what I'm seeing, but I'll show you a couple of alternatives. And actually, let me move this. We'll make this our first alternative. So if this is what you see, then where that had to come from was that my outer function, so I'll call this my shell function, s of x for shell. My shell function had to have been the square root of x, and my plug-in function p of x, oops, wrong color. Plug-in function p of x, if this is the case, had to have been 5 minus x squared. And that's how they were composed. However, you might not see it that way. Maybe you saw it this way. Maybe you see the square root of 5 minus x squared. If this is the case, then my shell function would be the square root of 5 minus x. And my plug-in function would be x squared. So there are going to be different ways that you can see these be decomposed. And it's your choice. So let's look at this last one. If we look at this last one as 4 divided by 3 minus x. Oh no, I'm sorry, I shouldn't have written x. Maybe we see this as 4 divided by 3 minus the square root of 4 plus x squared. In that case, the shell function would be 4 over 3 minus x, and the plug-in would be the square root of 4 plus x squared. There are numerous other ways you can look at this. Maybe it's something as crazy as this is how you let 3 minus the square root of 4 plus, and then maybe x squared, like that. In that case, your shell function would be 4 over 3 minus the square root of 4 plus x, and your plug-in would be x squared. So other ways you can do it. That's all I have for you for this lesson. I hope that this was helpful for you. Let me know if you have any questions.